Okay, so in this new section, we finally see Fermat's theorem, or what is also known as Fermat's little theorem. This name has been given to the result to distinguish it from Fermat's last theorem or Fermat's great theorem, the famous one that Andrew Wiles proved. Well, this result, which is known to most of us, was for the first time communicated by Fermat to one of his contemporaries named Frenicle de Bessy. And in his characteristic style, Fermat offered no proof. He commented that the proof is just too long to be sent. See, in those times, it's not just Fermat, but usually people were secretive about their discoveries. They just would announce that they found something and that's it. They won't really offer any explanation or anything like that as to how what they found is true or not. They will simply announce that I found this and that's it. But it's not like what we do nowadays. Nowadays we are happy to show others what we find if we find anything. So we don't really know whether Fermat really had a proof which was correct, but the first proof was published by Leonhard Euler. Although in an unpublished manuscript, Leibniz left a proof, so he should also be credited. Okay, so let's see the statement. Although we know, most of us know what Fermat's theorem states, but still let's see the statement. So here, P is a prime and A is an integer which is not divisible by P. For example, you can take P to be 3 and say A is 4. A need not be prime, A may be or may not be prime. A is some integer which is not divisible by P. Then A to the power P minus 1 is congruent to 1 modulo P. Or another way of stating this is that P divides the difference of A to the power P minus 1 and 1. So let's now see how we can prove this. So the proof starts by considering these integers. A, 2A, 3A, all these multiples of A up to P minus 1 times A. Now our claim about this list of integers is that when divided by P, they leave different remainders, distinct remainders. But before we prove that claim and make that claim and then prove it, let us also note something else. Note that P does not divide any of these integers. P does not divide IA for this type of i's. The question is why? Well, that's because P is a prime. So if P divides IA, you know by a previous result that P has to divide I or P has to divide A. Now it's already given that P does not divide A. And also, these inequalities make sure that P does not divide I. Why? Because I is a positive integer strictly less than P. How can it divide? How can it be divisible by P? So, another way of stating this is that whenever any such integer, any such multiple is divided by P, the remainder is not 0. It is something, but it's not 0. And now we make that claim. We claim that the above integers leave distinct remainders when divided by p. Now we have to prove this claim. Suppose not. Suppose this claim is false. Then some RA and SA from this list leave the same remainder when divided by P. In other words, they will be congruent to each other modulo P. We know that when they leave the same remainder, they become congruent to each other modulo that number by which you are doing the division. So, then there exists some R and S which are distinct but also within this range. Such that RA is congruent to SA modulo P. All right. Now, since P does not divide A and P is prime, we have this, that A and P are relatively prime. That is because when a prime number is given and some integer A is given, exactly one of these two things happens. Either the prime number divides the integer or it does not divide the integer. And when it does not divide the integer, then it becomes relatively prime to that integer. We have already seen this many times. That is why it happens, so I am not going into that now. But you know from the theory of congruences that when you have something which is present on both sides of a congruence and that is relatively prime to the modulus, then you can cancel it from both sides. Hence, R is congruent to S mod P. This, however, is not true. Why? But before we see why, how can we rewrite this in terms of divisibility? This means that P divides S minus R. Well, you can also say it divides R minus S, but S minus R is more convenient for us due to this inequality. This means P divides S minus R. But let us now see what type of number S minus R is. First of all, because R is less than S, S minus R is a positive integer. If you want, you can write 0 less than S minus R, or if you want, you can also write 1 less than or equal to S minus R. It's up to you. They mean the same thing. Now note that r is positive actually, see, and we are subtracting it from s. So obviously s minus r will be less than s, and s itself is less than or equal to p minus 1, and p minus 1 is less than p. This means that s minus r is a positive integer and less than p, but such a number is not divisible by p. No such number can be divisible by p. So this is a contradiction and proves that our supposition is wrong. What was our supposition? Namely that the claim we made there is false. So that means the claim has to be true. Hence the claim. But now what is the implication of this claim? How many numbers did we have in that list? Let us recall, okay. Whenever I write a dashed line like this and then again write something below that and then again write a dashed line, that part is not included in the proof. That is only for our understanding. These were the numbers that we considered in the list. Already we have noted that none of them is divisible by p, which means that when you divide these numbers by p, you never get the remainder 0. And at the same time, we have just now proved that they leave distinct remainders. Now, how many remainders are there when you divide something by p? These are the remainders. Among these, this is already ruled out. So we are left with p minus 1 remainders. And we are saying that these p minus 1 numbers, when divided by p, leave distinct remainders, which means that those remainders have to be exactly these remainders in some order. I mean, we are not saying that when you divide a by p, you will get 1 as remainder. When you divide 2a by p, you will get 2 as remainder. That we can't say. We don't really know. It will depend entirely on what a actually is. But in some permutation, these remainders will come. Each one will come exactly once, because these are the available remainders except this one, and the remainders have to be distinct. So by the pigeonhole principle, they have to be the remainders. Now we can express this by writing like this. So a 2a p minus 1a leave the remainders this in some order. When divided by p. In the language of congruence, this means that a is congruent to something from here, mod p. 2a is congruent to something else from here, mod p. 3a is congruent to something else, again, mod p. Now, if we and everything will appear in those congruences exactly once on the right hand sides of those congruences. Now, if you multiply all these congruences, what will you get? So, multiplying all these congruences, we are going to get something like this: a times 2a times 3a and so on, p minus 1a is congruent to, because multiplication is commutative and associative, I mean we are talking about ordinary multiplication. So, although I don't know in what order these things will appear as remainders of these numbers when divided by p, but I can bring the order back to the natural order: 1, 2, 3, p minus 1, mod p. Okay. This will imply what? If we simplify things a little bit, how many a's do we have here? 1, 2, 3 up to p minus 1. So, a to the power p minus 1. So, that's how this number appears. Times 1 times 2 times 3 up to p minus 1. What is that thing? P minus 1 factorial. The right hand side is just p minus 1 factorial modulo p. So, we are not quite there, we just have to cancel p minus 1 factorial from both sides, then we will get our desired congruence. But can we do that? Well, we can do that provided p and p minus 1 factorial are relatively prime. Are they relatively prime? They will be if p does not divide p minus 1 factorial, and that is true. Since p does not divide p minus 1 factorial, we have this. The GCD of p minus 1 factorial and p is 1, and that's why we can cancel. And after the cancellation, we get our desired thing. Oh, and why does p not divide p minus 1 factorial? Because if you write what p minus 1 factorial really is, it is this, right? Now, if p divides this, then since p is prime, p has to divide at least one of the factors, which however is false. All of these are positive integers less than p, so none of them is divisible by p. That is why. So, this completes the proof and gives us Fermat's little theorem. Now, there is a corollary to this which gets rid of that condition that p does not divide a. It says something similar, but for any a. Is there any no number? It's just a corollary. Let p be a prime number and a be an integer. Then a may be divisible by p, may not be divisible by p, we don't know. The result doesn't get affected. Then a to the power p is congruent to a modulo P. Fermat's theorem is so useful. I mean, it's a beautiful result, but besides that, it is used to reduce large numbers like this. Okay, so it becomes very useful when dealing with congruences, when simplifying congruences. There is a generalization of this result due to Euler, which also maybe you know, where you see a use of Euler's phi function. We will get to that at one point. How to prove this? So the proof considers two cases. If P really divides A, then obviously P also divides A to the power P. So A to the power P becomes congruent to 0 modulo P. But also A is congruent to 0 mod P. So that's how the claim in this case is true. If, however, P does not divide A, then by the above theorem, A to the power P minus 1 is congruent to 1 modulo P. So multiply both sides of this congruence by A. You can always multiply. It's only when cancelling something from both sides you have to be careful. This implies this. Okay, so that's the corollary. We are going to use the theorem as well as this corollary heavily later on when we really do heavy stuff with congruences. And the generalization of this theorem due to Euler will be even more useful. Okay, so we will see these things, and we will also see other things, in fact, what comes next after these things in the next number theory video. Actually, we are going to see another proof of this same result, Fermat's theorem, but that is by induction. That is I should not say number theoretic because it's about number theory, but that uses induction and binomial theorem. Okay, so we are going to see that proof as well. But anyway, let me just end the video here itself. Our next upload is this, when do we upload next? It's Friday, no? Friday, Saturday, Sunday and Monday. So on Friday we again have calculus. So see you with that on Friday. Until then, this is me, Lucifer from a mathematical group. Have a nice day.